Okay, this is video 9 of our sequence in basic circuit analysis, lesson 9, and today we are looking at Thevenin's theorem. Thevenin's theorem, and that's the only thing we're going to look at in this video. Okay, but let me start by motivating the need for Thevenin's theorem first. So imagine that you had some complex circuit, and we can say this circuit has maybe some independent sources. Independent sources, maybe some dependent sources. Okay, and some resistors. And I'll let you think about how all of these things are connected. Maybe just imagine some complicated circuit. All right, but this box represents that circuit. Okay, it's usually the case in circuits that that circuit will have an output, right? And we'll say a two-terminal output. And we connect different things to that circuit, and we're interested in what happens to that thing. In other words, a load resistor, for example, when I connect RL to the circuit. So how much voltage does it get? How much current does it get? How much power does it absorb? All that good stuff. Here's an example. Suppose you're at your house and you've got your wall outlet. So in this box is your wall, and then your wall is not a two-terminal device, it's a three-terminal. But suppose your wall was a two-terminal device. You plug in one appliance, right? And you get some voltage and some current. But now, let's say you remove that appliance. Maybe that was a washing machine. You remove the washing machine from the outlet, and you plug in a different appliance, maybe a toaster or a microwave. Okay, so you're changing RL. So we're going to illustrate that with an arrow through RL. So you're changing RL, okay, with different appliances, and you're interested in how much voltage is going to develop across that load, call that VL, okay, and how much current is that load going to draw, call that IL, from the circuit that's inside your wall. Now, in this situation, we never changed anything. We never changed anything inside your wall. This all stayed the same. So now imagine that you've got this complicated circuit and you've got this resistor connected there, and you analyze this complicated circuit once for when the resistor was a washing machine. Okay, and now you've changed the washing machine to a toaster. So you've changed RL. Are you going to analyze the circuit all again from scratch? Well, hopefully not. And Thevenin's theorem gives us a method for avoiding this unnecessary recalculation when just the output is changing. The output resistor in this case is changing. Everything inside is staying the same. Thevenin's theorem is going to allow us to take this entire circuit in the box and just reduce it, if you want to think of it that way, as just a voltage source, an independent voltage source, call that VTH for Thevenin, in series with a resistor, call that RTH for Thevenin. And here are our two terminals. Right? So Thevenin's theorem says that any circuit with independent sources, dependent sources, and resistors can be reduced, or there's an equivalent circuit like this, such that now when I connect those appliances to this circuit, well, remember what equivalent circuit means. It means that the voltage-current relationships stay the same. So these voltages and these currents will be the same as in this case if I do the transformation correctly. That is, can I find the Thevenin equivalent circuit of this complicated circuit so that I can just write this circuit instead. Now, if I change RL here, maybe the washing machine was 1 kiloohm, okay, and then the toaster is 10 kiloohms, right? Well, this circuit is pretty easy to analyze. I think you would agree. So I would rather analyze this circuit for each load resistor than potentially a complicated circuit for each load resistor. Okay, and Thevenin's theorem allows us to do that. Okay, before we continue, you might be asking at this point, especially if you're new to circuits, how useful is a circuit that is comprised of only independent, dependent sources and resistors? Well, admittedly, not very useful. We're just kind of learning at this point. But later on in the course, we're going to learn two more components called capacitors and inductors. And it turns out that everything that we learn in this course, such as Thevenin's theorem, can be applied to circuits with capacitors and inductors as well. So how useful is a circuit that is built upon resistors, capacitors, inductors, and sources? And it turns out you can build pretty useful things out of those components. Okay, now let's get into the mechanics of finding the Thevenin voltage and the Thevenin equivalent resistance. All right. So remember, if these two things are going to be equivalent circuits, then no matter what I connect to the output, okay, in either case, I have to get the same voltage VL and the same current IL. Okay, so let me connect something very particular, actually very trivial. I'm going to connect nothing. That is, I'm going to connect an open circuit. Okay, so something very particular here I'm connecting. All right, now notice in this case, when I don't connect anything at those terminals, there's no current that's flowing. IL is 0. So if IL is 0, there's no voltage drop across our Thevenin. So the voltage at the output terminals, VL, is the same voltage as the Thevenin voltage, VTH. Again, because there's no drop across this resistor. There's nothing isolating V Thevenin from the output. So right away we see that to get V Thevenin, we're going to find the open circuit voltage. Okay, so if there is something connected to the output of the circuit, we're going to remove it, thus making an open circuit. And we're going to find the voltage at the output terminals. Okay, call that open circuit voltage VOC. So it must be true then that the open circuit voltage is the Thevenin voltage. Again, if I connect an open circuit here, no voltage drop, I would measure the Thevenin voltage. So those two things are the same. So sometimes you'll hear me or other people say open circuit voltage. Sometimes you'll hear me or other people say Thevenin voltage. They're essentially the same thing. All right, well, the next thing we need then in the transformation is the Thevenin resistance. And notice in this circuit, if I turn off, so there are actually going to be two cases. So we'll say to find our Thevenin. Okay, there are going to be two cases, and the previous video illustrates why there are two cases. But we need to handle dependent sources and independent sources differently, separately, I should say. So in this circuit here, this simple circuit, notice that if I turn off the independent source. That is, I make this a short circuit. Then the resistance looking into the output terminals is simply the Thevenin resistance. Okay, so to find the Thevenin resistance, if the circuit, we'll say if the original circuit, the complicated circuit, if the original circuit, so that's this box, contains no dependent sources, then we can turn off all independent sources and find the equivalent resistance Req at the output. Then we know RTH is equal to that equivalent resistance. Okay, there's a second case though. Case 2, if the original circuit contains dependent sources. Okay, then we have a different method, and I just want to illustrate that to you here. If I connect a short circuit to this circuit here, okay, and if I measure that current, call it ISC, okay, or it's also IL in that case, but because I'm connecting a short circuit to the output, we're going to call that ISC for short. Then notice the Thevenin resistance can be found in a different way. It must be, from Ohm's law, the Thevenin voltage, which is across the Thevenin resistance, divided by whatever that current is, ISC. Okay? This method works for any circuit containing these three things. So if the original circuit contains dependent sources, we can find the short circuit current first. Find the short circuit current ISC by connecting a short to the output. Then R Thevenin equals V Thevenin divided by ISC. Okay, so there are our two cases, and I do want to point out again that case 2, it's more work, but it does apply to all circuits, dependent or only independent. Case 1 only applies if there are no dependent sources, but it's less work. So you'll want to use case 1 if you can, otherwise you should use case 2. And finally, a little note here, I just want to say that it's possible to get a negative Thevenin resistance. If you do that, then that means the circuit in the box is actually supplying power to the output. So that's possible if you have dependent sources. Alright, so let's look at some examples now, some concrete examples, and we're going to start with only case 1 so you can get the general idea of what's happening here, and then we'll eventually look at case 2. Alright, so I'm going to leave these things up here, and I'm just going to draw the circuit down here. So I've got, let's say, 32 volts. And 4 ohms. 12 ohms. Two amps. 1 ohm. Okay, and we'll say that here's the load resistor. Here's the load resistor, so that makes the output terminals right here. Alright, and we're going to find the Thevenin equivalent circuit. Okay. Alright, so up here, the first thing we said was to get the Thevenin voltage, we're going to find the open circuit voltage. Alright, well, here's my circuit, here's the output terminals, this is what was given to me. So, if something's connected there, let me remove what's connected, i.e., connect an open circuit, right? So there's an open circuit at the output, and I want to find this voltage. Call it VOC for open circuit voltage. So now I have to perform circuit analysis on this circuit to find that voltage. Alright, so now anything that I've learned before I can apply here. So think about KVL, KCL, combining resistors. So I can't really combine any resistors, but I will notice that mesh analysis is quite simple here. This guy on the right is not a mesh because of the open circuit. So that leaves me with this mesh, but I know that that is 2 amps. And then I've got this mesh. So this is my unknown here. Alright, so let me use mesh analysis to find I1. So we'll do KVL around mesh 1. Okay, so I'll start here. I've got 4 ohms times I1 plus 12 ohms times, and I1 and 2 amps are going with me, so this is I1 plus 2 amps. Then that puts me down here. I increased by 32, so I need a minus 32 volts there, equals 0. Okay, combining like terms, I have 16 ohms I1, and then I've got a 24 volts and a minus 32, so that makes 8 volts when I add it to the other side. Alright, so that implies that I1 is 1/2 of an amp. Okay, so if I've got 1/2 of an amp swirling around mesh 1, and I've got 2 amps swirling around mesh 2, then notice that this current here is how much? That branch current. What is that branch current? Well, that branch current is 1/2 plus 2. Right, so that's 2.5 amps there. So 2.5 amps, what's the voltage across that resistor then? So from Ohm's law, 12 ohms times 2.5 amps gives me 30 volts there. So that's 30 volts between this node and this node, right? Okay, well that's almost what I want, but I want the voltage between this node and the bottom node. But notice here, no current can flow through the 1 ohm resistor because it has no return path. So there's no current, there's no drop there. So the voltage that I'm looking for, this node to this node, VOC, is the same as 30 volts. This node to this node, again, because there's no drop across that 1 ohm resistor. So I've got it. I've got what I was looking for. VOC is 30 volts. Okay? All right. So the next thing I need then is the Thevenin equivalent resistance of the circuit. So notice our circuit here has no dependent sources. So case 1 applies, so we can turn off all independent sources and find the equivalent resistance at the output. So we're going to do that. So this 32 volts, actually I guess I'll redraw it. I'll redraw it up here. 32 volts, we're going to turn that off so it becomes a short. So here's my 4 ohms. Here's 12 ohms. And remember that current source becomes an open circuit when you turn it off. 0 current. So here's my 1 ohm resistor, and I want to find the resistance, the equivalent resistance there, and that is going to be equal to the Thevenin resistance. Alright, so notice that the 4 and the 12 are in parallel. That makes 3 ohms. And then that 3 ohms is in series with the 1 ohm, so this is 4 ohms. Therefore, the equivalent resistance then, and I'll erase this now, the equivalent circuit of the original is 30 volts in series with 4 ohms. That's it. And the claim is that whatever I connect here to the original circuit will draw the same voltage and current if I connect it over here to the Thevenin equivalent circuit. So let me demonstrate that to you by connecting let's connect a 6 ohm resistor. Let's connect a 6 ohm resistor and let's see if we can find the voltage and the current across and through that 6 ohm resistor. Okay, so let me clean up the original picture a little bit. Okay. All right. Well, I could use nodal analysis or mesh analysis. Let's use nodal analysis. It's been a while since we've used nodal analysis. So let's call this node up top Vx, and we'll call this on the bottom to be ground. And if that's ground, then this is 32 volts up here. 32 volts. So we're looking for Vx, and the 1 and the 6 ohms are in series, so that equivalently makes 7. Okay, so now I'm going to write a KCL, we're doing nodal analysis, at node X. Okay, so I'll guess that the currents are going this way, to the right, this one's going down, one's coming up, this one's going like this. Alright, so node X is this whole thing. Right? So going in is the 2 amps, and this guy, left to right, so this is 32 volts minus Vx over 4 ohms. And leaving is this one going down, so this is plus, equals Vx over 12 ohms, and then this one going down, so that's Vx over 7 ohms. Okay, so we can solve that then. Let's see, the common denominator here is what? It's not good. Okay, let's combine like terms. So we've got, if I get the negative 1/4 Vx to the other side, I'm left with 2 amps plus 32 over 4. 32 over 4 is 8 amps equals, and then for Vx I have Vx, I have 1 over 12 ohms plus 1 over 7 ohms plus 1 over 4 ohms. So this is 10 over here, so Vx is equal to 10 divided by 10 divided by 1 over 12 plus 1 over 7 plus 1 over 4. So 1 over 12 plus 1 over 7 plus 1 over 4. Okay? And so we've got 10 divided by 0.476. 476. Okay, so we've got 21 volts here. About 21.0 volts. 21 volts. Alright. So we'll add that to our figure. 21 volts. Now what's the voltage here, right? We want the voltage across the load. Well, we've got 21 volts across those 2 series resistors, so we can get the voltage across the load using voltage division. 21 volts across the series times the resistor whose voltage I'm interested in, 6 ohms, divided by the sum of the 2 series. So this makes 18 volts. 18 volts. How much current is through that resistor? IL from Ohm's law is 18 volts over 6 ohms, 3 amps. 3 amps through that resistor. Now, let's connect that resistor to the equivalent circuit up here, 6 ohms. Let's find the voltage across it. Right, so here's the VL. We can get VL quickly using voltage division. So we've got 30 volts now times the resistor whose voltage I'm interested in, 6 ohms, over the sum of the two, 6 ohms plus 4 ohms. So that makes 18 volts. Right? Notice that matches what we got here. Alright, and then for the current, again, we can use Ohm's law. Now that we know that there are 18 volts across that resistor, 18 volts divided by the 6 ohms, that gives us 3 amps. Same thing as what we got down here. Alright, but look at the effort it took to analyze this circuit, right? That was quite the effort. But look at how quickly we got the voltage and current here once we had the Thevenin equivalent circuit. So you can see now the utility of this. If I change 6 ohms now, so let's say I plug in a different resistor to the outlet, or different headphones to my MP3 player or something, right, where the circuit stays the same but the output resistor changes. Let's say I change that to 10 ohms. Do you want to analyze this circuit again? Or would you rather analyze this circuit again? Yeah, it's obvious. You want to analyze this guy. Change this to 10, redo the calculations, and that's what you're going to get when you analyze this circuit. But you won't need to do that. Alright, well, let's look at another example from case 1. Okay, remember, case 1 is when the circuit contains no dependent sources. Alright, so we'll do one more example from case 1. So we'll put 12 volts here, 6 ohms, two amps, six ohms, four ohms, and 1 ohm. And we'll say that the 1 ohm is the output resistor. So we'll say find the Thevenin equivalent circuit. Okay, so here, again, to find the Thevenin resistance, or excuse me, the Thevenin voltage, I'm going to remove the load resistor. So let's remove it, delete it, and what I need to do then is find the open circuit voltage there. Open circuit voltage. So I can do this, again, using any method I like. Let's try using mesh analysis. Call this I1, call this I2. Okay, and then from the independent current source there, we know that I1 plus I2 is equal to 2 amps, and so I1 is equal to 2 amps minus I2. Okay, so now if I do a KVL around the super mesh, okay, KVL around the super mesh, okay, I'll go clockwise. So the 6 ohm resistor is what I get to first, and here only I1 opposes me, so I'm going to write minus 2 amps plus I2, because this is minus I1. I1 opposes me. Then I come to the 6 ohm resistor up here, and this is 6 ohms times I2. So I'm going to write I2, and I'm going with I2, so that's okay. And then I have the 4 ohm resistor, so this is 4 ohms times I2, and I'm down here, and now I have an increase of 12 volts, so minus 12 volts equals 0. Okay, so if I combine like terms, I've got 6, 6, and 4, so that's 16 ohms I2. And the constant term, I have a minus 12 volts and a minus 12 volts. So add that to the other side, gives me 24 volts. So it looks like I2 is going to be 24 over 16 amps. And there's an 8 there. That's 3 halves. 3 halves amps. Okay, so if I want VOC, VOC is equal to, only I2 goes through the 4 ohm resistor. So this is 3 halves amps times 4 ohms. That gives me 6 volts. So that's the open circuit voltage, and again, remember, that is the Thevenin voltage as well. So now I want to find the Thevenin resistance. So that, again, this is case 1. Case 1, so we can turn off all of the independent sources and find the equivalent resistance looking in to the output terminals. So if I turn off the 12 volt source, right, that makes a open circuit. We've got 6 ohms there. The 2 amp source is an open circuit when you turn it off. 0 current. 6 ohms. 4 ohms. And this was our output here. And so we want the equivalent resistance there. Okay, remember the original circuit had this 1 ohm resistor here. We were calling that the load resistor. So remember, we're removing the load. Remove the load resistor to create that open circuit. Then find the equivalent resistance at the output terminals. Alright, so the 6 and the 6 are in series, that makes 12. The 12 and the 4 are in parallel, that makes 3. Okay, so we have both things that we need, the Thevenin voltage and the Thevenin resistance. So the equivalent circuit looks like this: 6 volts in series with 3 ohms. And now, if I want to connect that 1 ohm resistor to the output, I can analyze this circuit. Okay, so let me do that. Maybe we want to know what is the load voltage. Well, I can get that quickly using voltage division. 6 volts times 1 ohm over 1 ohm plus 3 ohms. So that's 6 over 4. So 3 halves volts. Okay, and maybe I'm interested in the load current. How much current is that resistor going to draw? So IL is, well, I have 6 volts across 4 ohms. So that is also 3 halves, but that's 3 halves amps of current. Now, again, I want to point out why this is useful. Take the original circuit, which had that 1 ohm resistor. Okay, if we analyze this circuit with the 1 ohm resistor in there, what we would find is that this voltage is 3 halves volts, and this current is 3/2 amps. But this circuit, the Thevenin equivalent circuit, is much simpler to analyze. Alright, so now let's look at a circuit with a dependent source, and with such a circuit we will have to apply case 2 and handle that dependent source carefully. So let's say we have 5 amps here and a 4 ohm resistor. Okay, 2 ohms, and we'll put the dependent source up top. Minus, plus, this will be 2 Vx, and Vx is the voltage here. This is 6 ohms and 2 ohms. Okay, and suppose our output is here, and we'll leave nothing attached to the output. So the question here is, or instructions are to find the Thevenin equivalent circuit. Okay. Well, so first, let's find the open circuit voltage. And the open circuit voltage, regardless of if you have dependent sources or not, is equal to the Thevenin voltage. It's only the resistance that changes our process. Okay, so we want to find the open circuit voltage, the voltage from here to here. All right, well, this is not easily done. Let's set this node to be ground right here. The reason I'm doing that is if this is 0, then this node is 2Vx. Oh, actually, let's back up. Let me set this node to be ground. Then this node is Vx, right? If this is 0 and the voltage across the 4 ohm increases by Vx, that puts this at Vx. Then this is 3Vx right here. Because if this is 1Vx, then this increases by 2Vx, so that makes this 3Vx, this voltage here. So we actually have all, I mean, we don't have Vx, of course, but other than that, we have all of the voltages that we need because of the voltage source here. Okay, so let's use nodal analysis then. So nodal analysis at this node, right? That's the unknown voltage, and we are going to make a supernode of this thing. There's our supernode. Alright, so we'll guess the currents. This goes down, this goes down. How much current goes through this 2 ohm resistor here? None, because it has no return path, because this is an open circuit. No current goes this way. Alright, we'll call this I1, call this I2. Okay, so KCL at the supernode Okay, well, we've got 5 coming in, 5 amps coming in, and we've got I1 and I2 leaving. I1 is Vx over 4 ohms, and I2 is 3Vx over 6 ohms. Okay, that's simple enough. The common denominator here is 12, so we can multiply by 12. That gives us 12. If we multiply by 12 ohms, then that gives us 60 volts equals 3Vx plus 6Vx. Right? Okay, so that's 9Vx. And Vx then is 60 over 9 volts. And there is a 3 there. So that's 20 thirds volts. Vx. So that's the voltage here, right, with respect to here. The voltage here is 3Vx. So this voltage is 20 volts then. 3Vx is 20 volts with respect to here, down here. No current through this resistor, the 2 ohm, so no voltage drop. That means the voltage that we're looking for, VOC, is also 20 volts. VOC equals 20 volts. This is presuming that you know circuit analysis so far. You've grasped the concepts that we've covered thus far in our sequence of videos. So if you don't see why this is 20 volts, pause it, think about it, go back to some other videos. No voltage drop means that's 20 volts. All right, so that is also the Thevenin voltage. Now comes the point where we need to find the Thevenin resistance. And because of the dependent source, we cannot just use the method we've been using. So now we have to change it up to case 2. So if you want to go back to your notes, what you wrote about case 2 says that we're going to connect a short circuit to the terminals, right? And that current there, I'll write it in red so it pops a little bit more. This current ISC, that's the short circuit current, and we need to find that short circuit current. Okay? All right, so this is not too bad because we've already done most of the legwork here for the KCl at the supernode. The only thing that changes now that there's a short there is there's another current that leaves. That's ISC. So let's do KCl again at the supernode. Okay, again, I'm using nodal analysis because mesh analysis here would take 1, 2, 3 equations, so we'd have to have a matrix and ugh. So we're going to use KCl, or nodal analysis. Alright, so I've got 5 amps coming in, Vx over 4 ohms coming out this way. I2 is 3Vx over 6 ohms. And I should point out that it's not necessarily 20 volts anymore. Now that we've connected a short circuit, we've changed the circuit. So it's 3Vx over 6 ohms. And then there's this current ISC that leaves as well. So that's 3Vx over 2 ohms. Okay, and so the common denominator here, 3 over 6 is 1/2. So the common denominator here is really 4 ohms. So let me multiply everything by 4. So this is 20 volts equals Vx plus 2Vx plus 6Vx. So that's 9. And so Vx is 20 over 9 volts. Okay? So that makes that 20 over 9. Then this guy is 3 times that. So this is 20 over 3 now. 20, I'll add it to the picture. 20 over 3 volts. Okay, so what is ISC? Well, there's 20 over 3 volts here, and here's ground. and then that goes across the 2 ohm resistor. So using Ohm's law, we have 20 over 3 volts divided by 2 ohms. That's 10/3 amps. Okay, so now indirectly we can get the Thevenin resistance. That's V Thevenin over ISC. So that's the 20 volts over 10/3 amps. So that gives us 60 over 10 ohms, or 6 ohms. Alright, so the Thevenin equivalent circuit now. So let me go back to the original picture. Alright, so I'll erase the short circuit. Okay, so here is our original picture. And its Thevenin equivalent circuit looks like this. 20 volts, 6 ohms. That's it. That's it. So now, again, let's look at the bigger picture. The bigger picture here is, here's my complex circuit. This original thing is the complex circuit. Now let's suppose I connect like maybe 20 ohms. Now I have to analyze this circuit. Find out how much voltage is across the 20 ohms, how much current is through the 20 ohms. Or I can just come to this simpler circuit and connect the 20 ohms there. Figure out how much voltage and current is across and through that resistor. Right? And maybe I change the appliance, or I change the load resistor. Maybe I instead of 20 ohms, maybe I connect 60 ohms. So do you want to analyze this circuit again, or would you rather analyze this circuit, the Thevenin equivalent circuit, again? This one. This one. Hooray! Right? This is the one we want to analyze. It's much simpler. So yes, we had to do the legwork, but once we get there, we can analyze this one instead of this guy. Alright, let's look at one more. So I'm going to erase this. Again, feel free to pause the video at any time if you want. Alright. So let's say we've got an independent voltage source of 6 volts and a dependent current source. Okay, this is 1.5 Vx, let's say 1.5 Ix, where Ix is this current up here. Ix. Okay, and here's the output terminals right here. Nothing's connected currently. So find the Thevenin equivalent circuit. Okay, nothing's connected, so there's an open right now. Alright. So we'll start by finding the open circuit voltage, which is the Thevenin voltage. Alright, we can do this quickly with maybe mesh analysis. So call this Ix, call this I1. Okay, we know that I1 plus Ix is equal to 1.5 Ix because of the current source, the shared current source. So that makes I1 equal to 0.5 Ix. Alright, so now we'll do KVL around the super mesh. Okay, we'll start here and we'll go clockwise. So I've got the 5 ohm resistor. The drop is 5 ohms. I1 opposes me, so I need negative I1, but I1 is 0.5 Ix, so I'll write negative 0.5 Ix. Then I have a drop of 3 ohms times Ix. And then a drop of 4 ohms times Ix. And then to get back to where I started, I have an increase of 6 volts. So minus 6 volts equals 0. Again, I did that quickly. I assume you know mesh analysis by this point. So now everything, let's combine the Ix's. So I've got 4 and 3 is 7, and a minus 2.5. So that's a minus 2.5. So that's a 4.5 Ix. Right, equals 6 volts. This should be ohms there. Let me back up. 4.5 ohms times Ix equals 6 volts. Ix equals 6 volts divided by 4.5. So can we simplify that? 4.5 is 9 halves. So that is 12 volts over 9 ohms. There's a 3 there, so that's 4/3 amps. Okay, Ix is 4/3. So what's the open circuit voltage then? If I have 4/3 amps coming through, right? Well, through that 4 ohm resistor. So the open circuit voltage is 4/3 amps times 4 ohms, and that is 16/3 volts. And that's also, I want to point out, the Thevenin voltage. Alright, so now I need the short circuit current, right? Because I have a dependent source. This is case 2. If there is a dependent source, you have to find the resistance indirectly by first finding the short circuit current. Okay, that current there. Here I want to point out that the 4 ohm resistor is shorted. That is, it's connected to the same node now because of the short circuit. So there's no current that goes through that 4 ohm resistor. All of the current goes through the short circuit. So now it's this circuit I have to analyze. And again, this is not bad. We already have done the legwork. We're going to stick with KVL, right, to find this current. Not much changes. We have the 5 ohms. First of all, this relationship between the two currents is the same. Right? Then if I start up here and I go clockwise, I've got 5 ohms times negative 0.5 Ix. Then I'm here at this 3 ohm resistor, plus 3 ohms times Ix. Okay, now this resistor is shorted out, so it contributes nothing to this. There's no drop across it because it's in parallel with a short. So we're down here, and now I increase by 6 volts. And so here's my KCL equation, or excuse me, KVL. KVL around the super mesh. Alright, so I can combine like terms. I've got 3 ohms and I've got a minus 2.5 ohms, so that makes 0.5 ohms times Ix equals 6 volts. So Ix is equal to 12 amps. Alright, so in this figure, Ix is this current that's circling around this mesh. None of Ix goes through the 4 ohms, So this is also ISC. See? So if I want the Thevenin resistance then, this is 16/3 volts divided by 12 amps. So that's 16 over 3 times 12. Okay, there's a 4 there at least. So this is 4 over 3 times 3 is 9. 4 over 9 ohms. 4 over 9 ohms. So the Thevenin equivalent circuit is 16/3 volts in series with 49 ohms. Right? And again, I want to point out that's for the original circuit, so I'll erase the short circuit. Okay, so for this original circuit, here's its Thevenin equivalent circuit, right here. So, again, now if you're interested in, what happens if I connect a resistor here, call it RL, well, just connect the resistor here instead and analyze this circuit.